Matrix multiplication mayhem. The secret life of matrix products. In problem 11, we're tasked with prove the equations 52, 53, and 58, which are the product of a transpose of a product rather, and then we have the adjoint of a product, and of course the inverse of a product. Then in the second part, we're tasked with show that the product of two unitary matrices is unitary. Interesting and very valuable. Under what conditions is the product of two Hermitian matrices Hermitian? C, or I guess this is D, is the sum of two unitary matrices necessarily unitary? Interesting question. What do you think? And then the last part, is the sum of two Hermitian matrices always Hermitian? Now let's go ahead, put your bets in the comments below on what you think about the last two specifically, and then we'll get on to proving parts A, B, C, and then D and E will be fun to work through. All right, so part A. So to prove the transpose product property, let's consider the definitions. Here we have the product ST, which have dimensions Ki thanks to the transpose. Now, if we take the transpose again on this, that equates to us switching the row and columns, much like we saw a couple questions ago. Now, that being said, if I take a transpose and I take another transpose, the two transposes are going to undo each other by definition. So that leaves us with the product ST with the dimensions IK. Cool. Now what we can do is kind of revisit this concept here that we saw in the matrix multiplication video, where we saw that I took the row and I multiplied it to the column and it looked like a dot product. And in that essence, what we see is the summation notation for matrix multiplication. So what we're going to do is sum over the indices j that are matching inside, because we need to have the two matching inside for the results to be IK. That being said, we're going to sum over all such indices s and t that make up the dimensions of these two things. That being said, if I were to take the transpose of s and t independently, that would require that I switch ij here and jk here. That's what we see here. But in order to sum over them in a dot product sense, we have to put the j's together on the inside. So that requires us to move this t to this side. As a result, this looks like the definition of the individual transpose within the confines of Ki. So that being said, we have the same dimensions Ki, so we see that the transpose of a product is the product of the transposes, but in reverse order, a thing that will continue to come up again and again and again. And this leads us straight through the adjoint or Hermitian adjoint or Hermitian conjugate, or just the dagger product property. So if I take two matrices S and T and I take their dagger or adjoint, knowing that the adjoint is equal to the transpose and the conjugate, I know that this transpose product equals this up here, so I can plug that in right there, no problem. Now I see we are in reverse order, each transposed, and now I just need to take the conjugate. But the conjugate only affects the elements of S and T by switching the sign on the I, so it's not like we have a dimensional mix match going on. That being said, I can apply this conjugate to both matrices independently, and that's what I see here. But now I notice that I have a transpose, conjugate, and that leads us back to the dagger operator, and we're good to go. We see that once again, the dagger of a product is the product of the daggers, but in reverse order. Very interesting. Again, this reverse order keeps coming back because of dimensionality. Now, the last thing to prove here is to consider the inverse product property. So what we first need to consider is that S and T are invertible. So things like have a non-zero determinant, for example. That could be a check on the infinite checklist that seemingly exists. That being said, to prove this, we know we can make use of the associativity property thanks to the vector space axioms, things like that. So because of this, what we're allowed to do here is I know I want to focus on this product S and T. That being said, I could multiply by S inverse here to peel off this S and T inverse here to peel off this t. But multiplying on the left-hand side by these two things makes this look like a product. As a result, using associativity of product and product, I could focus on this middle product here, S inverse S. And in order to be an inverse matrix, I have to multiply the original matrix back and get the identity. So S inverse S gives me the identity here. Now I could multiply this identity to this t and get back t because of the definition, or I could multiply this inverse t into the identity and get the inverse. Either way, I'm good to go. Associativity doesn't matter, or associativity tells us it doesn't matter. That being said, I'm left with t inverse t, which gives us the identity again. So now that I have this associativity construction here, what I can do is go ahead and use this right-hand side and this left-hand side and reuse associativity, but with the inverse of this product. So I see I have t inverse S inverse as its own product, and then I have st as the product, but I can now multiply on the right-hand side by st inverse, st inverse. What that does is it allows us to group this thing with this thing and get the identity back as well. Now the identity times this inverse just gives us back this product inverse. So this product, this product here and this product here, the inverse product gives us the I, leaving us with t inverse S inverse times I equals the st inverse. So we see that the product of inverses is the inverse of a product, but again in reverse order. Very, very weird how this keeps happening, but again, dimensionality has to match. Moving on to the second part here. To prove that the unitary product property, we need to consider, well, two unitary matrices, U and W. By definition, to be unitary, we need the adjoint to equal the inverse. Okay, so if U and W satisfy these requisites, then we need to show that W times U dagger is equal to W U inverse. Now again, we could say I want something like V dagger equal V inverse, where V is equal to WU, if that helps you to see what we actually need. As a result, if I'm looking at this left-hand side, the product WU dagger, I know that I can go ahead, thanks to the transpose property of the dagger, multiply the products independently, but in reverse order. Now that I have the reverse order, I know that I can look in individuality, but in reverse order. I can look at the unitary property of U by itself, which is an inverse, W by itself, which is now an inverse, and then from our inverse property from just the last slide, we see that this can be the product of inverses is the inverse of the product, but in reverse order. And then I prove complete what I wanted to set out to do. Therefore, the product of two unitary matrices is indeed unitary. Very nice. The third part here, to prove the Hermitian product property, we need to consider, well, two Hermitian matrices. So H and J are Hermitian, and by definition, that means that the Hermitian conjugate, Hermitian adjoint, or just the adjoint, there's 1,000 words for it, is equal to itself. And we saw this time and time again throughout quantum mechanics. That being said, the goal here is that we want to show that the product HJ with the dagger is equal to HJ. How does this happen? Well, if we look at the product HJ dagger, we know that we can reverse the order and take the dagger of each individual matrix and then multiply them together. Okay, cool. But since J is Hermitian, J dagger goes to J. H is Hermitian, so H dagger goes to H. This is not exactly what we're looking for here and here. So this is where the condition that is going to require us to have in order for this to be Hermitian. So here, to achieve the desired result, the matrices H and J must commute, meaning that the product HJ is equal to HJ. Okay, JH equals HJ. This condition can be succinctly expressed using the commutator notation HJ equals 0. Because remember, the commutator was HJ minus JH, but if they commute, which is stated here, then they're equal matrices, so it equals 0. And this is more or less the landscape that is used throughout quantum mechanics, so it's very important to us. Consequently, we can state that if the product of two Hermitian matrices is Hermitian, that the product of two Hermitian matrices is Hermitian if and only if their commutator vanishes, i.e. ℏ equals 0. And again, we've seen this time and time again of importance. Think about the Heisenberg uncertainty principle for two operators, or the uncertainty principle in general, the generalized version for two operators. Very important for us. Now moving on to part D, where instead of products, we're dealing with sums. And to prove the sum of unitary matrices is not necessarily unitary, consider the following unitary matrices. Well, guess what? We had a couple of them in quantum mechanics, the Pauli spin matrices. Sigma x, sigma z as defined here, but it would hold for sigma y as well. The question we need to ask then is, if I add these two unitary matrices, do I get back a unitary matrix? So the sum here of the dagger would have to equal the sum of the inverse. Is this true? Well, let's take this part by part, focusing on the left-hand side first. So if we're focusing on the left-hand side, we see that we need to add sigma x and sigma y. We see that here, and then we'll take the inverse, or the dagger, excuse me. So to add them up, we have to add component-wise, 0, 1, 1, 0, 1, 0, 0, negative 1. Easy enough. That leaves us with an all-real matrix here, and we notice that we're symmetric about the main diagonal. So the dagger here, which causes us to take the transpose, if we draw our line on the main diagonal, flip the 1 and 1, well, we see we just get the same matrix. Also realizing that this is an all-real matrix, the conjugate doesn't affect it, so we're good to go. Now we need to ask, does this actually equal the inverse? Let's find out. So we need to add the things together first and find its inverse. Upon adding it element-wise, we see we get the same matrix that we did last time. Now we need to find its inverse. Now the inverse here can be found, since it's a 2 by 2, by 1 over the determinant of the matrix. And then we have to switch this A component with this D component, which is what we do here and here. And then we need to append the B and C components with negatives. That's what we did here and here. That being said, crisscross, we see 1 and negative 1. We see that here, 1 and 1. We see that here, take their difference. And then that gives us negative 1 here, minus 1 here. So we need to multiply this thing by negative 1/2. So all three of these negatives turn to positive. That one turns to negative. And we have a scale factor of 1/2. What this shows is that this is not equal to the dagger side of it. So in general, for two unitary matrices, their sum does not necessarily mean that they are unitary. Now, our final part here, part E, to prove the sum of Hermitian matrices is indeed Hermitian, we need to consider our Hermitian matrices again, H and J. This is the definition. And the question we need to ask and what we need to show is, if I add H and J together, take their dagger, does that lead me back to H and J? Well, indeed it does. Because if I see that I have H and J here, by the associativity and all the dimensionalities that we need for the dagger, we're good to apply this to each individual part. Distributivity allows that to happen as well. So we see that we have H dagger plus J dagger, and we see that by their definition, H dagger goes to H, J dagger goes to J, so we get back what we want and prove exactly what we want. Now, of course, let's see this in action with an example. So as an example, let's consider the Hermitian matrices, which were also the Pauli exclusion, or not Pauli exclusion, but Pauli spin matrices. Again, these matrices were highly important to us because they were Hermitian, unitary, traceless, have a determinant of 1, things like that. Very, very, very important. Or, yeah, negative 1, excuse me. Something like that. It was very, very important to us. So, nonetheless, what we see here is that the question we need to ask, once again, is if sigma x plus sigma z dagger, does that equal sigma x and sigma z? Well, the left-hand side, add them together like we did just a part ago, last part. We see component-wise addition leads us back to the all-real matrix, 1, 1, 1, negative 1. The dagger, transpose conjugate, does not affect it, so we're good to go there. Does this equal the sum? Well, I think we saw that it did. Run it through, we see that we get 1, 1, 1, negative 1 again. Although you could have seen that we had the 1, 1, 1, negative 1 before the dagger and after the dagger, so that should already prove it to you. But this is also a great way to show that left-hand side equals right-hand side, so we're good. and thus we know that the sum of two Hermitian matrices is indeed Hermitian. Very, very cool. Love to see it. Which, by the way, that sum of Hermitian, if I have two Hermitian operators, I get another Hermitian operator. Very important for us in quantum mechanics. That's why we love it. So if this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There's so much more to uncover, and I'd love to have you along for the journey. I just want to take a moment to thank my incredible Patreon supporters. Your support is truly the backbone of this channel. It's because of you that I'm able to keep creating these videos and diving deep into the fascinating world of physics with everyone. Your contributions make a real difference in helping me bring these concepts to life, and I'm so grateful to each of you for believing in this journey. And if any of you are interested in supporting the channel and joining our Patreon community, you can check out the link in the description below. Together we can keep exploring the wonders of science and discovering even more amazing things. As always, thank you for watching, and until next time, stay curious.